gamma is 1 over sigma. Why is gamma 1 over sigma? Well, there's a lot of kernels, and usually there's a scaling factor in front of the scalar product. And that's the gamma, but for the Gaussian kernel, there's not a scaling factor in front of the scalar product, but you divide by it, so gamma is 1 over sigma. Exactly. And then there's further variants. So one that should be mentioned is new support vector classifier, which penalizes for the fraction of violation above the margin. So you control for how many points can be on the other side, as opposed to penalizing each point separately being on one side. Bound constraint, just adds this constant. I'm not sure exactly how it is better or different or worse apart from this other term. I'm not sure whether this has been extensively studied, but I'm just mentioning it since it's there. And there's multi-class versions, interestingly. And there's multi-class versions of every classifier, which can be obtained in a way of having one class versus testing one class versus all others, or one versus the others, and then aggregating the results. But for support vector machines, there's actually versions that natively do multi-class by having penalties that are actually spectral or multi-class in a way that accounts for the different classes simultaneously. So if you have a multi-class classification problem, when one way would be to have 1 versus 1 or 1 versus all support vector classifier, or to directly use a multi-class version of the support vector machines people have come up with. There's two versions that can or that may or may not help you, and they come with their own penalty constants, of course.
So by multi-class, in terms of picture terms, in the diagram you showed where you had orange and green dots, yeah?
And frogs.
Sorry?
And frogs.
And frogs?
Or blue dots.
Okay.
So you have third class.
Okay, so then you will be able to see 3 boundaries.
Yes.
That's what you mean by multi.
Exactly.
So actually that
Well,
is quite a hard problem already. So at the moment, most of the development has been just to do 2 classes.
yes.
To separate 2 classes. But then you have more than 2 classes, and that becomes already problematic.
Yes. Speaking about multi-class, I actually don't have a slide about that, but I should. So if you have more than 2 classes, you can make any 2-class classifier in a multi-class classifier by one of the 2 following principles, which also applies to support vector machines, by the way. So either you create a number of 1 versus all classification problems. So each class is classified versus all other classes. Right. Then you apply the classifier, and then you count how often the point was classified in one class or the other. Right.
Mm-hmm.
And from say a majority or maximum score criterion, you assign the class with the highest score in this 1 versus all experiment. Right? So if it had said a lot of times other, it's not this class. And for one class it says it is this class, then that's the class you assign. The other way is 1 versus 1. So for each pair of classes, and you throw away all classes but the 2, you train a classifier. Now then you run all the classifiers on your new data point, and you count the number of times it says the 1 class. And then you assign the class which has been assigned the most time in using all classifiers. So you see this can become computationally intensive because the number of classifiers is linear in the number of classes for the 1 versus all, and squared in the number of classes for 1 versus 1 multi-class strategy. So hence it is quite nice if you have a method that already internally can deal with multi-class, like the Weston-Watkins multi-class support vector classifier.
It's funny because there's a lot of examples where the classic example of fruits, right? Lots of different types of fruits, but then that means that would not be binary classification problem, right?
No, right. That's true. I mean, neural networks deal with that nicely if you have a lot of classes, then, for example, in the last ALO, you have one output neuron for each class where you get the probability from. So, for example, neural networks also internally can deal nicely with the multi-class problem. Whereas a lot of classifiers are only designed for the two-class problem. Of course, you can make two-class classifiers in multi-class, but if you have a huge number of classes, neither one versus one or one versus all scales really well.
But when you have a multi-class system, can't you just use clustering?
And that's
Try to address
unsupervised.
that.
That's unsupervised, yeah. It will give you, it's hard, it's a harder problem, right? You don't know the
Yeah.
labels.
Or you can always do k-nearest neighbors, for example. It's also
Oh, something like that, yeah.
If you list, say, the learners in MLR, there's going to be, so there will be this table which tells you can you do two-class, can you do multi-class, and then there is some learners which can intrinsically already cope well with the multi-class scenario. K-nearest neighbors, you just need to take the majority vote. Okay, so it's going to be the distance matrix, which is not easy to get, but the number of classes is not really a problem there.
We expect probably lowest scores in unsupervised learning versus supervised algorithms, right?
What do you mean, lower scores?
Lower accuracy, because it's like unsupervised. So it's like,
Yeah, but k-nearest neighbors is not unsupervised, it's supervised. I think you're missing this under k-mean.
yeah, sorry, yes, sorry. I was,
Yes. Same first name, K. Right, and k-nearest neighbors is assigned the next, the majority class from k-nearest neighbors. Okay, questions about this list of support vector classifier variants? I'm going to give you the slides so you can.
So in principle, again, also the support vector classifiers, those are there to make the process easier and better work. But so it's made, it makes the problem easier to solve, right?
Yeah.
In itself, it doesn't give you
So essentially
real insight in the data, but it does because it is faster. It's you get better.
It's non-linear.
Yeah,
It's one of the best families of classifiers that you can find if you use it if you tune it properly and use the Gaussian kernel, for example, or if you use a polynomial kernel. So on this slide, there's essentially just two types of support vector machines. So the two classes, the multi-class, the CSVC, the one with the simple penalty, would be possibly the first you would use if you have a two-class problem. If you have a multi-class problem, well, you can do one versus all CSVC or Weston-Watkins. Now the new SVC, so I have rarely seen it to be better than the CSVC, but sometimes if you have extreme outlier behavior, it does help because it does not, because it penalizes by the number of violations.
Yeah, so it's non-linear, so which is great, of course. But the whole representation in terms of these vectors, etc., or also with the kernel, the representation, internal representation that is being used in the so-called black box.
Yes, it is a black box. Yes.
That is not being used. You don't get to see that if you use the method.
But one thing you have is the support vectors. The support vectors being those data points for which the coefficients alpha are non-zero. So these support vectors are boundary prototypes. So you can have a look at them, though often it doesn't tell you a lot.
It doesn't have
So you get a set of boundary prototypes in the end if that makes sense in the application. But the model itself is partly also due to the interpretation of local smoothing. If you use the Gaussian kernel, it does not necessarily tell you a lot about the structure of the model. So it's more a smart way of interpolating without actually sort of scientifically learning from the model. So to answer question one can use the model, but it will not tell you by itself what
It's not that, that the data is represented for the end user in a nicer way that visually you can better see it or whatever.
Well, if you do principal components with the kernel method, you get a 2D picture of the data. That's one of many methods that give you a 2D picture of the data points scattered here and there. But it's not necessarily something that will give you stringent scientific conclusions visualization. So it's one more class of supervised classification. More black than white noise.
Well, internally it does it, but you don't get to see it.
Maybe not as black as neural networks are, but still white, black, grayish. Okay, so I'm going to skip these slides, but I will share them with you. So support vector classifiers for regression intuitively work in the way that instead of having multiple classes, you try to find a function around which in the margin all points lie. So you have the y-axis, so you're trying to find the function with the margin inside which most of the data points lie on the y-axis, and you can again derive optimization problems from the same principle, but I won't bore you with the actual derivation of the optimization problems. Put them on the slides if you want to work through them. But it's the principle for regression clear to everyone? It's not two classes, so it's not separating, but it's approximating. But apart from that, you also have the margin idea. You can also use this for anomaly detection. Now you have one class, and you want to detect outliers. And the idea is that you separate a region of the space. So this does not make a lot of sense if the separator is linear. But if it is non-linear, you know it will be a region that is surrounded or walled off by the separating function. And so you try to find a region of space in which most points lie. And if something you see outside this region, you classify this as an anomaly, as an outlier. Again, same variation on the same principle, quadratic optimization with a linear constraint. Linear constraints now given by being close to the other points or not. Okay. Also, I've added now 2 slides of kernel ridge regression. So for those of you interested to follow through the computation, so this linear algebra 101 or 201, why are these 2 equations for linear regression the same? So why can you flip x dx to x xt and then compute the inverse? So why can you replace the inner product matrix of the outer product matrix? The principle behind it, in essence, is that the eigenvalues of x xt are the same as the eigenvalues of x dx. That's one possible way to derive it, and that's one possible way to get the duality, say, that is behind ridge regression and kernel principal components. So I put the computation on this slide, but again, don't worry if you can't follow it right now. Just showing it to you when the slides are going to be shared. If you would like to work through it, the main result here is going to be that this expression, where we have x xt, the inner product matrix, is the same as this expression, where you have outer product matrix inside of the inverse. And one way to see it is by using this duality in the eigenvalue composition. Right. So, and then you have nice things such as if you let the regularization parameter go to 0, then you get the ordinary least regression parameter or the exact noise-free interpolator. Right. So much about kernels. I would say we have a short break until 11 a.m. and then we talk about neural networks. first thing